Formula One explained. Technology and strategy. Governing question. Why does aerodynamic performance, rather than engine power, define competitiveness in modern Formula One? Formula One is often discussed in terms of power. Engine output, top speed and acceleration are easy to observe, and they tend to dominate casual conversations about performance. However, in modern Formula One, outright engine power is rarely the decisive factor. Instead, competitiveness is primarily shaped by how effectively a car generates, controls, and sustains aerodynamic performance. In this episode, we will explain why aerodynamics has become the dominant performance differentiator in Formula One. We will explore how downforce influences lap time, why aerodynamic efficiency matters more than raw power, and how regulatory constraints have shifted engineering priorities over time. By the end of the episode, you should have a clearer understanding of why modern Formula One performance is defined less by horsepower and more by how air is managed around and beneath the car. To understand this, it is important to start with how lap time is actually created. A Formula One lap is not dominated by time spent at full throttle. Instead, a significant proportion of lap time is spent cornering, braking, and transitioning between phases of acceleration. In these phases, grip is the limiting factor. Grip determines how fast a car can turn, how late it can brake, and how early it can apply power on corner exit. Aerodynamics directly increases available grip. Downforce increases the vertical load on the tyres without increasing the car's mass. This allows the tyres to generate more lateral and longitudinal force, improving cornering speed, braking performance, and stability. Engine power, by contrast, primarily affects straight-line acceleration. Its influence is intermittent rather than continuous. As a result, a car with superior aerodynamic performance will often outperform a more powerful car over a full lap, even if it is slower in a straight line. Historically, the balance between power and aerodynamics has not always been the same. In earlier eras of Formula One, particularly before the hybrid power unit regulations introduced in 2014, differences in engine architecture and peak output were more visible. Engine performance could translate directly into lap time advantage, especially on power-sensitive circuits. However, even in those periods, aerodynamics remained critical. What has changed in the modern era is the relative weighting. Today's power units are tightly regulated. Fuel flow, energy deployment, and architecture are constrained. As a result, performance differences attributable purely to engine power are significantly smaller than in the past. Aerodynamics, however, remains an area where small improvements can produce meaningful lap time gains. Modern Formula One cars generate the majority of their downforce aerodynamically through a combination of wings, bodywork, and critically, the underfloor. Ground effect aerodynamics allows teams to accelerate airflow beneath the car, reducing pressure and effectively pulling the car toward the track surface. This approach produces high downforce with relatively low drag, improving aerodynamic efficiency. However, this efficiency comes with sensitivity. Ground effect systems are highly dependent on ride height, car attitude, and airflow quality. Small changes in suspension behaviour or track conditions can significantly alter aerodynamic performance. This is why aerodynamics cannot be treated as an isolated discipline. Suspension geometry influences ride height. Ride height affects underfloor airflow. Underfloor airflow determines downforce stability. Tyre behaviour adds another layer of complexity. As tyres wear, their effective diameter changes. This alters ride height and aerodynamic balance, even if the car's mechanical setup remains unchanged. As a result, aerodynamic performance evolves continuously over a race stint. Because of this sensitivity, engineers do not optimize for maximum peak downforce alone. A car that produces very high downforce in ideal conditions, but loses it unpredictably, will be difficult to drive. Inconsistent aerodynamic behaviour reduces driver confidence and increases tyre degradation. This is why engineers prioritize aerodynamic stability and repeatability. The goal is not to produce the highest possible downforce number, but to produce downforce that is consistent, predictable, and robust across varying conditions. This emphasis on consistency explains why some cars appear competitive across a wide range of circuits, while others struggle when conditions deviate from a narrow operating window. Aerodynamics also shapes race strategy. Aerodynamic performance is affected by turbulent airflow from other cars. When a car follows closely, disturbed airflow reduces downforce, particularly from wings. This affects braking distances, tyre temperatures, and cornering speed. As a result, aerodynamic behaviour influences overtaking difficulty, tyre degradation, pit stop strategy, and even qualifying approach. Regulatory changes in recent seasons have attempted to mitigate these effects by simplifying bodywork and shifting downforce generation toward the floor. These changes have altered how teams approach development. Rather than pursuing fragile peak solutions, teams increasingly prioritize aerodynamic robustness, designs that perform consistently in clean and disturbed airflow. Aerodynamic development is also strategically constrained. Wind tunnel usage, computational fluid dynamics, and manufacturing resources are regulated. Teams must decide where to allocate limited development capacity. Because aerodynamic changes often introduce unintended effects, development is rarely linear. An improvement in one area may introduce sensitivity elsewhere. Engineers must constantly balance performance potential against operational confidence. This makes aerodynamic development as much a decision-making challenge as a technical one. In modern Formula One, engine power establishes a baseline rather than a differentiator. What separates competitive cars is how effectively they generate, control, and sustain aerodynamic performance across a wide range of conditions. Aerodynamics defines not only how fast a car can be, but how consistently that performance can be delivered. It is this combination of efficiency, stability, and system integration that makes aerodynamics the defining factor in modern Formula One competitiveness. If you found this explanation useful, you can follow or subscribe to Formula One. Explained, Technology and Strategy for future episodes.